Okay, so a lot of this, is stuff that you would be able to figure out if you had the proper motivation and the proper time and a piece of paper and a pencil, and you were relaxed. You could figure out all this stuff. There's nothing new here. Nevertheless, I say figured out. You could predict it, but I'm going to tell you what we have done, what has been done a lot. It's going to fit very nicely in your head. And then we're going to end this water as a nucleophile section with why we would want to do this, why it makes sense. Okay, so we're going to talk about a nucleophile and a carbonyl carbon. Look at this here. We're going to talk about a carbonyl carbon and a nucleophile, and it's going to do exactly what you would think. You have to be constantly thinking about shape and polarity, right? All right, so first one we're going to consider is beautiful, water, and it's just what you would imagine. You got an oxygen, boom, right? So we've already seen why that's an electrophile, and that's going to go up. All right, so this is going to go into equilibrium with the product. So take a second and write out what that is. Now, show a generic mechanism. We're going to do, I think, like 4 versions of this in this one video. It's going to be a long video. And look for the similarities. Okay, so show a generic mechanism for water attacking an aldehyde or ketone, which I've just done below. Predict whether the nucleophilic attack is product favored or reactant favored. And you are constantly thinking about shape and polarity, right? All right, and the next question is, would the presence of an acid improve this reaction? So we've got some slides dedicated to this question here, so let's move on. What would an acid do, first of all? What would an acid do? Here. Okay, think about that for a second. All right, let's move on. Now, if water were to attack the carbonyl, what likely mechanism steps would follow? And would the overall process be faster? So I probably should have killed this slide. These are all questions we're going to address in the next couple slides. Look at this. If water were to attack a carbonyl, what would happen after that? Well, can I go back a slide? That would happen. Wham, right? Of course. Right? So if water were to attack the carbonyl, what likely mechanism steps would follow? Boom. And then would the overall process be fast or slow? Well, we have to figure out what's the fast or slow is going to be dictated by the energy of the transition state, right? As compared to the energy of the reactants. Will the overall process be product or reactant favored? And so now we're going to go on for some examples. So, if you have acetone, this you recognize, right? It's 1, 2, 3. Propane, 1, 2, 3, right? Propanone, 2 propanone. It can only be 2 propanone, right? Because if it were anyplace else, it would be an aldehyde. So, I mean, it can only be propanone could only be 2 propanone, so we might just call it propanone. Either way, acetone. Wow, look at this. This is heavily reactant favored. Look at this. Over almost 100% is reactant. It is in acetone with water. Looks like this. Almost 100%. So in formaldehyde, however, almost 100% is over here. What? They don't look that different. You have a trigonal planar carbonyl carbon, trigonal planar carbonyl carbon. What's the difference? Aha! I'm running my dryer behind me and my coffee pot next to me. Alkyl groups are electron donating, right? Alkyl groups are electron donating, and so that carbon, which has a partial positive on it, its partial positive, thank you so much, its partial positive is mollified by the electron donors. Boom. Oh, look at that. Please recognize that. This partial positive, right here, let me get a different color to wake you up in case you're struggling being interested, which is, all right, look at that. that has got a partial positive on it. But if you've got electron donors, it's not as partial positive, so it's not as good a target, and hence we don't have as much. Okay. Oh, plus it's crowded, right? CH3 is much bigger than a hydrogen, right? Well, hydrogen is not electron donating, right? If the electronegativity of carbon is 2.5 and hydrogen is about 2.2, you know, if anything, it's electron withdrawing, right? No, I'm sorry. It is slightly donating, but barely. So it hardly has anything to donate, right? It's slightly less. I beg your pardon. So either way, this has got a much bigger partial positive charge and it's less crowded. So both shape, crowded, and polarity right? So both of those favor formaldehyde getting the nucleophilic attack. All right. Now what about hexafluoroacetone? You say something about the shape and about the polarity of those. All right. Now, let's keep rolling. Oh, there's one more thing I want you to consider. Entropy. Here's my shape. Here's my polarity. This is the language of Klein, by the way. Induction and resonance, okay? And sterics is what he might say for shape. All right, but there's one more factor, and that's entropy. Yeah, I'm not going to say anything about that. Think about that. What are the entropic issues here? All right, now let's look at the first mechanism, and every one of these mechanisms you need to know. I think it's 20.3, 20.4, 20.5, maybe 20.6. You need to know these. These are going to fit very nicely in your head, and they're going to teach you about what electrons are going to do also, so it's going to really help you. Okay, so you have nucleophilic attack if you're dealing with a base catalyzed hydration. Look at that. Boom. And that's going to go up here, of course. You know that's a good nucleophile. It's hydroxide. You've seen it many times. And once that's been pushed up, you have an alkoxide here, right? Which is basic. And so if there's a water molecule running past, it's going to grab a proton, and you'll have a diol. It's called a gem diol, I think. Oh, it's been a long time since I used that word. I probably should have looked it up before I said it. But I'm going to write it here, and you can look it up. Is that a gem diol? Look that up. It's been too long since I've used that word. All right, now this is the picture we had in the previous slide. How's it? I should have gotten rid of this, I guess, because we're going to repeat. I should have gotten rid of this slide because it's just exactly what I had in the previous slide, right? How does base increase the rate of the reaction? And so remember now, rate is dictated by activation energy, right? And this is the energy of the transition state. So draw the transition state and draw the reactants, and that will tell you about rate. Okay? All right, now the reaction can also be catalyzed as by an acid, and this is mechanism 20.4. I might have 2 slides dedicated to this too. Probably should have gotten rid of one. All right, mechanism 20.4. So what does an acid do? You've seen this before. You have a pair of electrons and a proton donor. There's my acid. Proton transfer. You've seen that many times before. Please love that. All right, and then a nucleophilic attack after that. Why is this a better electrophile? I think we said this in the last slide. It's a better electrophile. Why? Draw out the resonance hybrid. If I just slow down just a little bit, my handwriting gets very pretty. Draw out the resonance hybrid of this. Draw it out. Draw out the resonance hybrid of that. And you'll see why this is a better electrophile than this is. Not better electrophile. Okay? Now, that said, the water comes in, attacks the carbon, and then it's left with a partial positive charge, which is going to now act like an acid to a passing water molecule. And so this then becomes H3O+. We started with H3O+, hydronium. This is then going to become hydronium again, and that's why we call it catalyzed, right? Because we started with an acid, we end with an acid, and also we get our diol here, which I think is a gem diol. Maybe it's vicinal, I don't know. All right. Look that up. It's a diol. I'll look it up when I'm done here. No, I'm going to look it up now. I'm going to keep those notes. Gem diol. The internet's a little bit slow here. Yep. Gem diol. Geminal diol. That's exactly what that is. Okay, good. Good. Thank you, Google. I love you. My friend. I'll be back. All right. So this is a gem diol. Whoops, what happened? How did that happen? Oh, let's go back to red. All right, so we're gem diol, and you get that by base catalysis and by acid catalysis. And the acid is shown here. We first of all protonate, that's step one, and then we get nucleophilic attack. That's step two. This is also part of step two, right? That's concerted, and then we get proton transfer again. All right. So the nucleophilic attack really is the star show here. Let me go back a slide and look at the base catalyzed. Remember this one? There's the nucleophilic attack. There's the star of our show. Nucleophilic attack. We're going to see it over and over and over and over again. So please like it. All right. Now, how does the acid increase the rate of reaction? I'm going to ask you to do this thing again, okay? Do that again. The activation energy. Draw out the structure of the transition state. That's not the intermediate. That's the transition state. Okay? And that will help you. That will help you appreciate what it does for the rate. Okay, now, acetal. Here's a new term. This is one thing you could not have guessed, all right? You could not have guessed that this is called an acetal, that we're going to need it, or why it's valuable. All right, so now we're getting into new information. So an alcohol acts exactly the same way. Let me go back a slide and say, when I see water, I oftentimes think of an old friend of mine who's structured very similarly, right? You see that? Boom, boom. Boom, boom. Very similar structure. So what we learn about water, we can oftentimes apply to alcohols. And so we come here and go, okay, yawn, I get it. If I gave you a pencil and a piece of paper and a little bit of pressure, you would be able to draw the mechanism for this, because it's going to be proton transfers, it's going to be nucleophilic attack, resonance may play some role, right? Let's look at the mechanism together. It's mechanism 20.5. It's on the next slide. So if it's acid catalyzed, did we say it was acid catalyzed here? We did. Acid catalyzed. If it's acid catalyzed, you can have a proton transfer, so that we have a better electrophile here, right? Now with the better electrophile, we've got the alcohol coming in. Boom. Once it comes in, it's got a formal charge, and so it's going to act like an acid, right? So the base, which was over here, this is now a base. This guy comes here. Boom. He says, oh, I'll take your proton. Proton transfer happens over and over and over and over and over again. So try to get a sense of why that's obvious, okay? So that comes in. Oh, by the way, we didn't know we were going here. You knew you were going there, right? Because you memorized it. So we get this nucleophilic attack. Now when we come here, you might think, oh, well, we could just have, these guys could come back down again and this guy could get kicked off. Or, which could happen. But we're not in acidic conditions. It couldn't, because you got positives. You wouldn't get a negative leaving group. But you could have protonation of this guy again. Right? Actually, which is a better base? This guy or this guy? Well, they're pretty similar. But since you know you're going here, and we're going to do that with, and we're going to push it with Le Chatelier's principle. Okay, so it'd be okay, I think, for you to just simply memorize that the hydroxyl gets the proton because you're going in this direction and you're doing it with Le Chatelier's principle. I can describe that in more detail in class if you ask me. If you're okay memorizing it, then do that. All right. So the hydroxyl comes, takes that proton. Again, we've got an acid used, acid regenerated, acid used, acid be regenerated down here again, right? Okay, so the acid is used. That becomes a fantastic leaving group. You've seen this before. You saw this with elimination of alcohols. How do you spell it? That's terrible. Elimination. Okay? So elimination of alcohols, you've seen that before. Now watch what happens. What's the leaving group here? What's the name of that leaving group? Water, right? So these electrons come down, and you've got some weird looking structure. Actually, it's not that different than what we've seen before. But suppose if it's weird, just memorize it. You've got to have water as the leaving group. You've got to have something kicking it off, and that's it right there. So once that kicks it off, then a water molecule comes in, nucleophilic attack, or not a water molecule, it's an alcohol, right? Look at there. Alcohol comes in. You know you're going in this direction, so you've got to get the other alcohol on there. He comes in, kicks off those electrons up. Now you've got an extra proton, which gets deprotonated, and bam, there is your acetal. Wow. Oh, it's lovely. Okay, so I'm going to argue that every one of these steps is something you've seen before, with a possible exception of this guy, which is just ugly, right? That you haven't seen before, so you may need to memorize that. This is going to help you both in this chapter and in another chapter too. We're going to see another structure that's kind of like that. So look at it, like it, love it. All right, so this is how acetals are formed. I think it's mechanism 20.5, and you need to know it. All right. Now, after the hemiacetal is protonated in mechanism 20.5. Look at this. It's talking about this section right, this right here. I got a question about this in the next slide. Okay, watch this. After the hemiacetal is protonated in mechanism 20.5, the water group leaves. Why is the water group pushed out intramolecularly? Right? You see that? This does not happen. You could just have another alcohol come in like that. But does not happen. Why? Give you a hint. Remember SN1s? Tertiary carbons were not attacked via SN2. Why? Why is that? It's too crowded. It's too crowded. I don't remember if I got rid of the next slide. Let's look and see if that's given again. Nope, it's not. Okay, so that's the point. You get it? That the water molecule has got to get pushed out with these guys instead. Because it's just too crowded for this guy to come in here. And you know what? This is just like an elimination. Just like E1, E2. Just like it. Okay? So when I told you in semester 1 that if you like these mechanisms, substitution, addition, elimination, you're gonna be in a good position later. This is what I meant. Stuff like this. Okay, now let's look at some examples. So if you take formaldehyde and you put this in a bath of ethanol, where's my marker? Put this in a bath of ethanol, acid catalyzed, you're going to get this acetal. Okay? I don't even know the name of it. Doesn't matter. Now, if you take acetone in ethanol and you add acid to it, it's going to be reactant favored. Okay? So, knowing that, I will tell you that we oftentimes use this diol. This is a vicinal diol. We use this for a cool purpose, which is about to come up, okay? For now, can you see how this would happen? Draw this mechanism. Write this out. Write out this mechanism and bring it to class. Write this mech out. Bring to class. Write that mechanism out and bring it to class. Okay, and you have an acetal here. And it's got a weird shape, almost looks like a little person, right? Can you see a head with a couple ears here? But don't be distracted by that. Do not be overwhelmed by these weird shapes. Get your eyeballs used to them. The best way to do it is to look at it, to draw it, and to practice with it, and you'll get used to it. It won't be so bad. All right, so draw that full mechanism out. How we take this is, I think, is ethylene glycol and a carbonyl carbon, and if we treat this with the acid, we're going to get this guy here. Okay, what's the hybridization of that carbon right there? SP blank. What is it? What's the hybridization of that carbon right there? SP what? You tell me. All right. Okay. Practice with Skill Builder 20.2 and come back for the last couple of slides of this video. Good questions. How do each of these affect? And you've been using these all along. You've got to get on the bike and ride it. I'm not going to tell you the answer right now. Bring it to class. Ask me. You've got to try this. I'm a nag, aren't I? I know it. I'm sorry. All right. Now, how do we put these on and off easily? All right. So if we take this carbonyl compound and we put it in a bath of ethylene glycol and acid, we're going to get this. An acetal. Okay? Now, if we take that stuff and we wash it with water and acid in acidic conditions, we can get our ketone back. Both the forward and the backward reactions are acid catalyzed. How does the presence of water, and this is important, if you practice those questions I asked you to do in the previous slide, this I think will be obvious to you. How does the presence of water affect which side, the equilibrium will favor? I hope I asked you this on the quiz. I don't take that as a promise or a threat or anything else. It'd be such a good question. I hope you're ready for it. Okay, so I think that's 2 slides left with a couple questions here. Now we can use acetal. Watch this. And here's the big deal. Acetal as protecting groups. We can use acetals to selectively protect an aldehyde or ketone from reacting in the presence of other electrophiles. So suppose you have a reaction. I'm going to call reaction X. Here's reaction X. Suppose you have a reaction that it's something that's more reactive, that X is more reactive than esters, then you're going to get some reaction here, right? But suppose that so in other words, you're going to get a reaction here too, right? But suppose that you wanted to only have it at the ester. What could you do? Go with a different color here. Protect this guy. Reaction. Gobbledygook down here. Gobbledygook and get this guy back. We've done this before. Protect. Deprotect. Right? And that's the way you could get reaction at only. So you have a way to reduce an ester, right, to an alcohol. But that way to do that, but that method also reduces ketones, right? So if you want that, you're gonna have to protect that. You're gonna cap that first and then uncap it. I hope that's helpful. I think there's one more slide here with a question. If there's not, I'm just gonna cut that part off and say goodbye. I'll say goodbye now. Okay, not goodbye. Let's look at this. You work this out. Pause the video, and I'll work it out also. So pause the video. When you come back, I will work it out with you. Okay. Let me suppose that you did pause the video. All right. If you paused it, then you've got some notes in front of you, and you want to see what I got. So if you take this and you treat it with ethylene glycol, an acid, and you somehow remove water, maybe by boiling, right? Okay. If you remove the water, maybe by boiling this stuff off, watch what happens now. You're going to cap this guy, right? So you're going to get a little Martian. It's not a Martian. You're a guy with a crew cut, right? It looks like a Marine. Okay. I was not in the Marines. Okay, so I don't know if that's a good thing or a bad thing. I know it's cool to be in the Marines, but I don't know if a Marine. I don't know if a Marine would take that as a compliment or not. I do know the Marines are cool, so let me leave it at that. Some of you are rolling your eyes. I know. I'm sorry. All right. My son was in the Army, but I still don't know. Okay, now if we do that, and then we do some reaction to cut this guy, right? Reduce. Find a reducing agent. Give you a hint. Chapter 13. Number 1, we have to reduce. Number 2, we've got to deprotect. Okay? And then, wow, this is cool. Look at this. There's a couple steps that go here. A couple steps. That is slick. No, actually, we can do this in one step. We can do this in one step. Oh, that's so cool. I'm not going to tell you what this is. Bring this question to class. Bring the mechanism to class. Show mechanism. Oh, wow, that's really good. Bring that to class. All right. I think that's it. I'm going to say goodbye now, and I'm going to advance the slide. If there's one more slide, then we'll see it, and then we'll say goodbye again. Goodbye.